please introduce yourself and just give a little bit about your background and your research focus.
Sure. So my name is Michel Belyk. I'm a senior lecturer at Edge Hill University in the UK. My research is focused on the human voice and all of the things that it can do and how it does them. So that'll combine some behavior about how people use the voice, neuroscience about how it's controlled, and a bit of evolution about why humans have voices and brains in this particular way, that we engage in these unusual behaviors like speech and singing.
Great. Yeah. So you focus a bit on the psychology and sociology part of the voice as well. But I thought maybe just to get there, let's talk about the physics of how we understand the speech first, right? When I think about somebody speaking or somebody singing, there's a ton of information contained in that act, basically. When somebody's singing, you can, if you know the song, you can kind of hum along with the pitch. So there's that. You don't even need to know the words, but you can understand the song just through the change in the frequencies that the person is creating. And then in addition to that, they say words, and that's all something extra that they're doing in addition to creating those pitches, right? They're changing the tone or something with their voice. And then if you're familiar with the person, or maybe if they're a famous singer, you can even recognize the person just based on their voice, by some unique thing that's going on there. And then if they're a talented singer, they can even change sort of the tone to give different impressions, make you feel different emotions, all kinds of things that's going on when somebody is singing. And people really do understand this intuitively, but I don't think many people really have an understanding of what's going on physically when all these things are happening with all the information that's in this sound wave.
Yeah, that's really insightful. And that's indeed actually part of what attracts me to the voice as something to research. So even though the signal itself is quite low dimensional, right? We can model it as a single sort of waveform over time, but it contains a huge amount of information. So all of speech, all of singing, expressing more emotions than the face does, identifying you as a person, so you can identify voices individually. Lots of paralinguistic stuff, so things that you don't realize that you're doing alongside speaking. So for example, we add in little cues indicating when you're done speaking, so you can sort of yield the turn to the other person to speak, questions and statements, these sorts of things. There's huge amounts of information in what is superficially a really simple signal, which is very appealing from my perspective.
Mm-hmm. Great. Yeah. And we'll hopefully get to there by the end. People will understand what's going on there. But let's just start very simply at the beginning, right? Talk about what sound is, and just sort of the physics of how we create and understand what a sound is.
Right. So sounds are pressure waves traveling through air. So we want to not think of it as the air itself moving. So the air doesn't go very far. That would be more like wind. But this is more like you have some movement in space of some part of your body. So maybe that's part of the speech making system that we'll talk about later. Maybe it's clicking your fingers, but something physically moves, which causes a bunch of air molecules to bunch up in place. So you've got lots of molecules together. That's a high pressure zone now. So right, there's high pressure in the air. That's going to correct itself by moving some of those molecules to an adjacent area with lower pressure. Now that new area has higher pressure than its neighbor, and this proceeds so on and so forth. And so you get not the air moving very far, but the air pressure moving, propagating through space away from the sound source.
Mm-hmm. And we call them sound waves because they travel in waves, maybe in medium that we're more familiar with seeing visually, something like an ocean wave or something like that, where the molecules themselves aren't traveling with the wave, but they're kind of translating their movement to adjacent parts of the water, right?
That's right, exactly like how if you observe something floating in the ocean or something, you'll see it going up and down along with the waves, but not actually moving all that far. We also want to be mindful that we can be talking about transverse waves, so waves that go left and right, or longitudinal waves that travel forward and back. So a nice analogy that we can make that many people may be familiar with from, say, the high school physics class is making waves with a slinky. So if you recall in high school, probably you had a partner in a slinky. You placed the slinky on the ground, and you both wiggled it back and forth, left and right. And this made a transverse wave. And how fast you wobbled the slinky determined how fast of a wave you made. And so that's sort of more like what that wave in the ocean looks like. But our pressure waves in air look more like these longitudinal waves. So you can also make a wave with the slinky by pulling it back and forth. So you can have the links in the slinky bunch up together in some places, that's your high pressure zone, and be spread apart in others, that's your low pressure zone. And you can observe the high pressure traveling along the slinky. That's a nice analogy, I think, for what air is doing when we make sound.
And then that pressure wave interacts with something in our ears and oscillates it back and forth. And that's how we understand the vibration, the wave pattern, and receive that information that's being, transmitted through the air, right?
Exactly, yeah. I do a little bit of physics in the form of acoustics, but a lot of that is what we might call bioacoustics. So talking about how the physical body interacts with these physical acoustical forces. So sometimes that's on the production side, how we make the sounds, and other times that's on the hearing side, how those acoustical sounds are transformed into something that you perceive at the level of the ear.
Okay, and then when we start to think about how objects actually produce sound, right? We think of them, somehow they get agitated, they get excited, and they start to vibrate and create these pressure waves. And most objects tend to move back and forth when they're excited like this at some sort of regular intervals, right? You could think about sort of the easy one to visualize is a string that's, guitar string that's tied at both ends, and you pluck it and it vibrates back and forth, and it's just a given frequency. It doesn't change a whole lot. And if you pluck it harder, it still doesn't change that frequency. It just gets a little bit louder, basically. It changes the amplitude.
Exactly. So this guitar string is a nice analogy for us. So you have some physical object that begins to vibrate. It vibrates at a frequency that's determined by the physical properties of the string. So you'll have longer, looser, heavier strings making a low pitch, shorter, tighter, lighter strings making a high pitch. So it's vibrating, that's causing air to move, right? So when the string moves to the right, let's say, it's making a high pressure zone to its right because it's bunched a bunch of air together, and that pressure is going to ripple away in that direction. At the same time, on the left, it's made a low pressure zone because it's evacuated some space. The air molecules that were to its left are now occupying lots of space with the same number of molecules, so it's low pressure. And that then pulls in molecules that were further away, which now makes a new low pressure zone, and that ripples out the other way. So you have this sort of oscillation between high pressure and low pressure rippling away from the sound source.
Good. And I'd like to introduce another idea just sort of at the beginning here so we get a handle on it, and that's the idea of interference. So if we think about, say, maybe a speaker producing a wave, because it's easy to visualize, you just have this wall that's pushing air back and forth to create a wave. And then if you introduce another speaker, that creates a second wave, and basically you're adding these two waves together, and it's kind of a simple mathematical addition, right? And depending on how they interact with each other, if they're going at the same, then you add them. If they're going opposite, then basically you subtract them. And so this is really an important concept if we want to understand how the information that we hear is being transmitted.
Yeah, that's exactly right. So you get this sort of linear combination of sounds produced by different speakers, right? So they can either be in phase, in which case they'll add together and they just become louder. They can be perfectly out of phase, in which case they cancel each other out. Or they can have some weird phase relationship, in which case they're going to do something funky. And something that's interesting about that as well is if you think about your auditory environment, it never has just one sound source, right? There's lots and lots of stuff going on, and it's all going to arrive at your ear at some point where it will add together additively or destructively, depending on what's going on, to make some very complex sound wave. And that's the signal that ends up getting received by you at the sort of end of the acoustic chain.
And we can even pick out multiple sources, which I always find interesting. We can kind of hear things from different, even though it's all combined in sort of the same wave. Okay, good. Maybe a good way to visualize this then, sort of what creates this complex sound wave is to go back to the string and understand that if you look closer, when you pluck that string that we're talking about, it resonates at a frequency, but also it kind of wobbles around a little bit, and there's other things going on with that string. It's resonating in different ways as well. It's not just that bass sort of back and forth, right?
Exactly. So we talked about that string earlier, how its physical properties would determine the pitch that it, sorry, the frequency that it will best vibrate at. So we tend to call that the fundamental frequency. And so that usually is going to be some frequency with a wavelength that has either two high pressure zones where the string ends or two low pressure zones. And so it has sort of this sort of stable phase relationship. But that works equally well for a frequency that's twice as much, right? So for example, if you think of a sine wave, drawing sine waves badly in the air, if you think of a sine wave traveling through this string, at some points that sine wave reaches sort of zero pressure. If you have the length of that wave be just right, those zero pressure points line up exactly with where the string ends. But you could accomplish that just as well by having two of those sine waves shorter, right? So twice the frequency and just have two of them, or four times the frequency and have four of them, and so on and so forth. So what you tend to have is not just a single sine wave going through the string, but you get that single sine wave plus twice its frequency plus fourth frequency and so on and so forth. And we call these harmonics. So you'll get vibrations at the fundamental frequency, which is more or less pitch, corresponds to the pitch that you hear, plus more energy at harmonics, so integer multiples of that fundamental frequency. And the relative combination amount of energy at each of those harmonics is different depending, again, on some of the features of the instrument. And that's what we end up, at the end of the day, hearing as timbre, because you've learned that the harmonic relationship for strings on a guitar, for example, are different than the strings on a piano. Even if they're playing the same note, these harmonics have different amplitudes, we'll say. And you've learned over the course of your life that this one set of amplitudes tends to come from guitars, and another one comes from pianos.
And the harmonics really do dominate the frequencies that you hear in a single sort of produced sound wave, right? There's not a lot of random frequencies getting into something that's resonating and producing sound. It really is those multiples of the base frequency, right?
Exactly. So we can think of these objects, really any object that you'd find musically useful, you can think of them as frequency-specific amplifiers, right? So any sound that meets, or any frequency or wavelength that meets that criterion I said, that it has the right pressure relationships at the end of the object, will be amplified quite a lot. And any sound that doesn't meet that criterion will tend to be diminished, because it will end up having weird phase relationships, and you'll have lots of different waves canceling each other out through that destructive interference. And so, yeah, for those three reasons, you get lots of energy at these harmonics, and then no or little energy between them.
And there's ways we can kind of prove and understand that mathematically, right? So we can look at basically dissect a sound wave and kind of understand what's going on there. That's called a Fourier analysis, and I think you probably have a good explanation. Do you want to just give a summary primer for people who aren't familiar? Talk about
Sure.
Fourier transforms.
Sure. So the same way that we can talk about different sound sources combining together, so simple waves combining together to make a complex wave, we can take a complex wave and break it down into the simple waveforms that would have made it. So Fourier analysis is the sort of mathematical, analytical way of doing that we might do with a recorded sound. But you actually have a GUI biological Fourier transformer in your ear. which I think this blew me away when I sort of learned about how this works. So even though I'm more of a voice person than an ear person, maybe we'll do a little bit on the ear now to just get this Fourier a bit. So when a sound arrives at your ear, right? So those pressure fluctuations arrive at your ear, making some complicated oscillation. They hit your eardrum, so it's going to transform oscillations of pressure back into oscillations of movement. So the drum moves back and forth. That's going to wiggle some bones, some really teeny tiny bones that work as an amplifier. So they just make the oscillations bigger. And then at the end of those bones, we get to the cochlea, which is the organ of hearing. And it has a special membrane called the basilar membrane with a very specific and special shape that makes it a biological Fourier transform machine, which is awesome. So it has, you can picture like a rug. Okay, so picture like a very long rug on the ground, and you could, lift the rug and bring it down and send a wave rippling down it. There are some frequencies at which you could probably keep doing that to make a wave continue going down, but if you went too slow or too fast, it would break down. If you made a thinner rug or heavier rug or longer rug, whatever, you could change the properties of it, and the waves that would be good at transferring would change. Now, what if you made the rug asymmetrical? So at one end, it's skinny and tight. At the other end, it's fat and floppy. What you get is when you send a wave down, it hits a specific point where the wave that you sent matches the properties of the rug, and you get a big amplification of movement just for that spot. And now if we send not just a single sine wave through, but a complicated wave, like what arrives at your ear, you get big spikes at all of the locations where there are frequencies in that sound wave.
Wow. So you're triggering different places spatially instead of just trying to interpret the wave directly, I guess. You're kind of translating it. Oh, wow.
Exactly. So that complex wave turns into a spatial code in the cochlea where low frequencies are at one end, high frequencies are at the other end. And each sort of spot on that membrane is attached to some sensory neurons, right? So they pull a little plug that activates an ion channel, neurons fire, and now we've gone from pressure waves in the air to information in your brain. And so this basilar membrane really acts like, you can think of it either as a Fourier transform or as a bank of filters. That would be a different way to think of it, right? As a bank of filters, each of which selectively responds to a very narrow frequency band.
Yeah, so basically what you're doing then is you're doing some sort of transformation to create this complex wave that's filled with many frequencies and dissect them, and you're able to basically categorize or plot each frequency then, or quantify, I guess would be the word, to quantify the amplitude of each frequency then. Yeah, so that really informs the tone, the character of the sound that we hear. And we, at least in my experience, we don't have very good words to describe the different kinds of sounds that we hear. Musicians are probably familiar with some of them, maybe like they'll talk about a full sound or a bright or tinny sound, but we don't really get much beyond that except to use analogies to things that we hear. Do you have some words that you use in like your research to communicate how we transmit these different qualities of sound?
Yeah, I actually don't, and I'm not actually convinced that those words are used consistently, full, bright, etc.
I agree.
I've tried to talk with musicians a little bit about this to see if we could sort of unpack like some spectral profile that would, line up with brightness or something. And I too find language somewhat limiting in terms of talking about this, really because that's not a part of the perceptual space that we deal with day to day, right? You have some sort of higher level interpretation of the sound, like this was a word, or this was Matt's voice, or this was a trombone, or a certain emotion that's sort of more relevant to us, and we have really deep sort of semantic, lexicon to deal with. whereas the sort of lower level attributes of the sound are things that come much less naturally to us, and we have these sort of discipline-specific bits of jargon like, full, bright, or dark and nasal,
Yeah.
that are less clear, I think, to a novice and to me.
Yeah, agreed. So let's move on to the tone. So that gives the characterization of if you're sustaining a note, right? If I'm just to hold a pitch there or to play a note on an instrument. But when we're talking, this is changing through time, right? There's some time element to all the things that we were just talking about as well.
So now you're going to let me talking about my favorite thing, which is how we make the voice. We're going to try and break this into 3 pieces, right? So 3 sort of muscular systems that we use to make the sort of time-varying, really complicated sound that ends up being speech. So one is going to be the lungs, right? So you have the diaphragm is a muscle that sits below the lungs and sort of push them up and down. And you have muscles between your ribs that sort of pull each rib down, sort of crushing the lungs a little bit. And so this makes a kind of bellows, right? So when these things come apart, the lungs expand, that makes a vacuum, you inhale. We don't tend to use that for communication very much. Other species do. For some reason, humans aren't into it. The interesting stuff happens when we go the opposite. So we bring the ribs down, bring the diaphragm up, crushing the lungs. That creates high pressure in the lungs. Air is going to start flowing outwards. So that's sort of the source of mechanical power for all of your sort of vocal sound production. So that's where the energy is going to come from. So this air is whooshing up from the lungs through your airway. It's not doing anything periodic. It's not making any particularly interesting sound. This is just wind moving up. At about the level of the throat, so actually if you find your Adam's apple, you can find my favorite organ, the larynx. Sometimes we call this the voice box. And so this is now where your voice gets its periodicity, or where you're going to get the pitch of your voice. So the larynx has 2 membranes in it called the vocal folds. And you can do a few things with them, but the main things are you can move them into the airway or out of the airway. Right? So when they're out of the airway, air flows through freely. That's really nice for breathing. When they're in the airway, they actually constrict the passage of air quite a lot. And we can sort of put them entirely closed in the airway and have them quite taut. In which case what happens is air, sorry, you want to say something?
No, I was just wondering, is that associated sort of with, I guess, other muscles that we think of as tightening? You would constrict those muscles, and when you close that airway, then?
Yeah, so it does have a few small muscles in it, but most of what's happening is that these membranes are attached to some cartilages. So they're attached actually right behind your Adam's apple is one part of attachment, and so that's sort of fixed in place. And then it has the other side is attached to 2 cartilages sort of towards the back of the airway that are on hinges. So they sort of swing back and forth. And so you have a actually complicated set of muscles that swing these hinges back and forth, and those then swing the vocal folds into or out of the airway.
Yeah, maybe. I'm just thinking, so this is very sort of a complex structure. Do we want to start and talk about wind instruments a little bit first, just to, because for me, that's quite analogous to how we produce sound then. If you think about wind instruments, you're not resonating like a string or anything. What you're doing is you're forcing air through an opening that's opening and closing very quickly. And yeah, so it's maybe musical instruments are a good way to start, because people can visualize, like you can't see what's going on in people's throats, but you can kind of see the construction of a musical instrument and see how it produces a frequency, I guess, first.
What I actually like for this is, have you ever made like a comb and wax paper kazoo? Did you ever do that when you were a kid?
Yeah.
Yeah, so it's actually going to work a little bit like this, right? So you take the comb and you wrap wax paper around it, and you sort of blow on one end. And what this is going to do is it's going to make the 2 flaps of wax paper wiggle back and forth. right? So you're creating some pressure oscillations between your mouth and the comb that's traveling along the edges of the wax paper, and that's making both of them ripple back and forth, and then that ripple becomes an oscillating sound.
That one, you're kind of going around it as well. This, in your voice, you're basically forcing the air through a thing and it's opening and closing very quickly, right?
Exactly, exactly. So you get air building up below these vocal folds. Eventually, that pressure exceeds, the force keeping it closed, and you get sort of a burst of air coming through until the air pressure equalizes and they snap shut again. And then air pressure builds up again, and you repeat this cycle. So you get this cycle of air pressure building up and then a burst of air coming through and then closing. So that's as with basically all other sounds, an oscillation between high pressure and low pressure that's then filtering up from the lungs as just a sort of static movement and then becoming an oscillation at the larynx.
And then you can change it by flexing it and changing that tension a little bit, which is actually different than musical instruments, because most of them have sort of like, let's say a reed instrument, they kind of have a fixed tension at the top, and you change the pitch by lengthening the resonance structure, not by changing the tension on the resonator at the top. But the voice is different, I suppose, then?
Yeah, exactly. So then you're going to change the pitch of your voice basically by stretching or relaxing those vocal folds, right? So when you stretch them out, they become thin and taut, kind of like, the high-pitched strings on your guitar. And when you relax them, they become, floppy and floopy, kind of like the low-pitched strings on your guitar. And so actually you alluded there to the fact that your guitar has sort of these adjustable bits at the top, right? Those sort of tuning pins. And so you could imagine a world where you had a guitar that had only one string and all you did was change the tuning very rapidly. That's kind of what you're working with here, is using that sort of tuning pin on the guitar to make the string tighter or laxer. And if you could somehow find a way to do that fast enough that it was musically interesting, that would be sort of an analogy to what the voice does.
I have actually seen, they have bass instruments with like kind of a lever that you can pull and tighten it very quickly, and it kind of produces a cool twangy sound, right? I don't know if there's more you want to get into with the production, but then that all the structure in there relates to the tone and all the different frequencies that we were talking about, the way or the frequencies that are produced to create that sort of unique sound, right? So if you think about speaking sounds, you're adjusting sort of the machinery all up in your mouth, but all the way, all the way sort of in your upper body, I guess. And again, most people intuit it. They probably don't really understand what's going on when they're changing their mouth in this certain way to change the tone in this certain way. But we understand it, and we can produce these sounds very reliably.
Yeah, exactly. So we talked about the lungs as mechanical power. You can think of that as basically controlling amplitude, right? How loud you are. We talked about the larynx as an oscillator, which you can make low frequency or high frequencies. That's pitch of your voice. That sound that's your voice, that sort of pitched sound, as with the strings, has harmonics, right? So it's vibrating at a fundamental frequency that we typically hear as the pitch of our voice. So about 100 hertz for men and about 200 hertz for women. But then it also has energy at harmonics, integer multiples of your fundamental frequency. Now what happens is this sort of complex wave now with all these harmonics is traveling from the larynx up through the airway, through the mouth, towards your lips, and then out into the world where it can find someone's ear. But the mouth has a very complex shape, and it's a shape that we can change. And now that shape is going to also be a kind of resonator. So it's going to selectively amplify and dampen some of those harmonics in your voice. Sort of the same way that the same note played on like a guitar versus some form of violin or something. The shape of the body of these instruments has resonant properties that's going to selectively amplify some frequencies and dampen others. That's part of what gives it its distinct timbre. So now your mouth is going to have some complicated shape that imbues some distinct timbre onto the sound that you're making. And you use your articulatory muscles, so mostly your tongue, also your lips, to change that shape. So you selectively amplify some frequencies over others. And that's how you end up encoding the different sounds of speech, right? Is you're just pushing the voiced sound, this oscillation with many harmonics, through a complicated set of filters, of sort of acoustical amplifiers, you could say, that amplify some frequencies or others. Which ones happen to be amplified determines which speech sound we're talking about. And actually, we can do a quick little demo for this if you want, walking through a few consonants. So we're going to do 6 consonants. I'll ask you to say those consonants, and then think about where your tongue is when you say these. Okay?
Okay.
So let's do K and G. Ka, ga.
Ga. Okay.
Right. So you had a constriction in the back of your throat, sort of in the pharynx. Both of those were in the exact same place.
Wow, those are very subtle difference between those two sounds.
Yeah.
Yes.
Now if we do ta and da.
Ta, da. Okay. For
Right,
that
so
one, for me,
now-
yeah, the tongue's a little different, and there's sort of a delay in how it's used, I suppose.
Yeah. So now you've got the tongue sort of just behind the teeth in both of those cases. We'll do one more, and then I'll tell you why I think this is a good demo. So
Okay.
pa and ba.
Pa, ba. Okay. Yeah, those are very, very subtle
Right.
differences. I have a hard time understanding what the difference is actually.
Right. Exactly. So the differences are actually none. K and G, ka and ga, are articulated in the exact same way. Your tongue's doing the exact same thing. The only difference is that for the ga, the larynx starts to vibrate a bit earlier. So we call that yeah. For ta and da, they're actually identical, except for the D, the larynx starts to vibrate a little earlier. Pa and ba, same deal. The B, your larynx vibrates a little earlier, but they're articulated in exactly the same sort of way. Now, to give you this demo with one more that makes it much, much more obvious, I want you to hold, so find your Adam's apple, and then make the S sound, like the sound that a snake makes.
Sure.
Nothing. You probably got nothing out of that, right?
Right.
Now do the same thing, but make a Z sound. Just hold the Z like zebra. Do you feel a little vibration in your fingers there?
A little bit. Yeah.
Yeah, exactly. So that S and Z are produced with the exact same mouth position. It's just that in one case, the larynx is open, the larynx is open, air is passing through freely until it reaches the sort of lips, and then it starts to get perturbed. Whereas for that Z sound, the larynx is closed, you get vibration. And so it's this oscillatory voice sound hitting the same articulatory pattern and passing through the same filter. And so we have these sort of few dimensions that make up speech. One is whether your larynx is vibrating or not and when, and the other is the shape and position of your articulators. So if you go through that initial sequence of consonants again, just do ka, da, ba, you can feel sort of a movement from constriction toward the back, a little in the middle, and then right in the front. And then you can think about the shapes that makes inside your mouth, right? So you do the ka, you've got a small resonant chamber at the back of your throat and a big one in the front. When you do ba, it's all one big hole, right? It's one big resonant chamber from larynx to lips. And so where you make this constriction changes the shape of this resonator, which makes the sound different. And through development, you've learned to interpret those as different speech sounds.
Interesting. Okay, there's sort of two fun anecdotal examples that I like to use that might help illustrate or just be fun to talk about now that we have an idea of what's going on here. One is if you've ever seen musicians sometimes they'll play their instrument and connect a tube that goes into their mouth. It's not very common anymore, but like Peter Frampton was sort of
Frampton,
the
yeah, I
first
thought we
one,
were talking about
right?
Frampton, sure.
Yeah, yeah. So you put a generator, so you know it's your voice is no, or you're no longer producing the sound wave in the traditional way, but you're putting sound into your mouth and then changing the mouth, and that's the only thing that's basically creating these consonant sounds that we talked about. Although I guess the way we just talked about the differences in K's and G's, you probably can't do that with this sort of setup then.
Yeah, I mean, so what he's effectively doing is replacing the larynx with a guitar, right? Instead of having the larynx vibrate to make an oscillatory sound, the electric guitar is making some oscillator, which he's then putting in the mouth and using the shape of the mouth to sort of change the resonant characteristics. What he's probably using more than consonants, because yeah, those sort of stop the flow of air and make things a bit difficult, is he's probably doing something more like vowels. And this works the same way. So we can do a really easy demo is make the sound ah and think about where your tongue has gone.
Ah.
Right, so it's really low in your mouth and probably constricted quite back in the throat.
Yeah.
And then the letter E, or yeah, the sound E is in feet.
Feet. Yeah.
E, right? So the tongue's
Okay.
very forward, smashed up almost against the roof of your mouth. And again, this is just changing the shape of the resonator, amplifying different combinations of frequencies, which then the listeners learned is different vowels. And Peter Frampton can use to filter his guitar sound in different interesting ways.
So in that example, specifically, the ah probably lets more of the lower frequencies go through, whereas the E maybe cuts those ones and let the higher frequencies through. At least that's kind of my impression.
Roughly, yeah. So we tend to see these different configurations of the mouth that make different vowels. They tend to have 2 or 3 or maybe 4 bands of frequencies that they amplify well. So you can think of it as chopping up. So if you think of your vocal tract as a tube, right, from larynx to lips, by changing the shape of the tongue, you're kind of chopping it into 2 or maybe 3 smaller cavities, each of which has a special bandwidth that it's good at amplifying. And so, well spotted, the E is unusual in having one very high bandwidth. That's probably what you're picking up on. Yeah.
Okay, cool. Have you ever seen those voice modulators where you push something against your larynx and there's some sort of feedback and it creates, like, that's how you would, disguise your voice or something? That's kind of a fun little example of how you're changing something deeper in the sort of machinery to get a different and produce a different sound. Do you know much about how those work? Or
I know less about the voice changers, but you do sort of see the same thing as an aid for people who've had like a laryngectomy, for example. So if they had their larynx removed for some medical reason, they can no longer make the voiced sound that would produce speech. They can still move the articulator, so they could sort of whisper, but they can't, sort of project a voice. They would have trouble being heard. In which case, yeah, they can just place an external vibrator against the throat where the larynx sort of would have been, and that will create some oscillation, which then passes through the same articulatory filters we were talking about and shapes speech sounds in the same way. So it becomes like a substitute for the larynx.
And then one more thing I wanted to ask you about. Have you ever seen the talking piano on YouTube? Basically, it's this program, and it seems like it almost is just banging on keys. It's like this very sort of structured, changing the tone through time. It's not supposed to sound like music or anything, but it's supposed to sound like the sounds that we produce. And like we were saying with the Fourier, and you're deconstructing a sound into its constituent frequencies. This tries to add them together just very crudely on a piano and tries to add together all those frequencies to create sort of a talking sound and create some of these sounds that we produce by adding together all these different frequencies and then changing them over the time. And so it looks like these keys are just slamming down and moving all over the place. And it doesn't work that well, but like if you see the subtext underneath it, it's like, oh, okay, like I can kind of understand what's going on here.
Yeah, I mean, interesting. I could see how that would work with the right combination of keys, but it'd be hard to solve. It must be difficult. But yeah, I mean, the basic idea is that to our ears, a speech sound is made up of maybe 2 or 3 bandwidths where there's a lot of energy, right? So if you think of those harmonics as going through a really big sort of frequency space, and then you amplify a bunch of those harmonics, and then you dampen a bunch of other harmonics. And so which ones you amplify and which ones you dampen is going to shape which vowels you hear. So if you sort of arrange this piano in such a way that there's, a bunch of energy in the harmonics around 500 hertz and a bunch of other energy in the harmonics around 1500 hertz, or 5000 hertz, we'll say, then that will probably at some point start to sound a bit like a vowel, because that shares some attributes with what voices do.
Mhm. Okay, yeah, it's definitely not a great sort of one-to-one. Oh yes, I understand what this piano's saying, but it does sort of have its unique character of a voice too. It's really cool. So yeah, that's pretty good in-depth detail into the machinery and how we produce all these sounds. And for a lot of people, you're in the psychology department, so that's really just getting started, right? These are just the tools then you use to study social behavior and the language that we use. I'd love to get into some sort of the social aspects of how we communicate these different tone changes and how we understand them socially, right?
Sure. I mean, I can give you actually one that I've been working more on lately, which is that you may have noticed that some people sound larger than others, right? This is sort of a social aspect of our voices that we don't think about too much, but in hindsight seems somewhat obvious. And so part of that is we tend to think of as big people have lower pitched voices. And that's sort of maybe true. So it turns to be the case that at some point during development, you have a burst of testosterone. Testosterone has a side effect actually of making your larynx, your vocal folds, big and floppy, which then makes them vibrate at lower frequencies. So that's why you tend to think of really low pitched voices as sounding really like masculine and macho, because that probably does co-occur with people, especially men, who have large muscular bodies, because those are both things that are driven by developmental testosterone. The other thing that you can hear that's maybe less obvious to us is, so we've been talking about the vocal tract as a resonator. Well, taller people will have longer vocal tracts, which will mean it's a bigger resonator, which amplifies lower frequencies. And so then that's something that becomes sort of hard-coded in the way that you produce vocalization, is that you're just working with a bigger instrument, right? So, maybe you're more tuba than trombone or something like that. And so you sort of tend to amplify lower frequencies if you're a tall person, and that's something that you can hear rather easily.
Yeah, that's a good analogy, I think. So yeah, like a trombone and a trumpet can play the same note, but you can understand the differences.
Exactly, just because of the larger size of the instrument. This comes with an interesting social sort of element as well, though, in that the larynx doesn't just have a fixed position. We can actually wiggle it up and down a little bit, more with training, but we do it spontaneously. So for example, when you go to speak authoritatively, you tend to drop the pitch of your voice, but you also tend to drop the larynx down lower a little bit, which means you're working with a bigger resonator and you're simulating a taller and probably more dominant person. Likewise, when you're maybe, when you're talking to the boss, you want to be a little submissive, you might actually do the opposite a little bit, right? So you give a high, friendly pitch, hey, boss, we're on good terms, right? Maybe you raise the larynx a little bit to diminish yourself, and so you simulate a smaller, more demure person. This is something that we do sort of somewhat spontaneously. And so this sort of simulation of the size of your body through the size of your vocal tract is something that we think is happening in sort of dominance relationships. So I brought up, talking to the boss there, or maybe you have a subordinate that, you want to make sure you get them in line, you have the right relationship with. Maybe you drop the larynx and sound more dominant there. But it also works in mating contexts. So in right? So we judge people, how attractive people's voices are. Some voices are more attractive than others. And most of that just falls on gendery sorts of lines, right? Men tend to be perceived as more attractive if they have lower pitched voices. So again, that's that testosterone signal we talked about. Or if they have larger sounding vocal tracts, because that should just be a bigger dude. Whereas women tend to be perceived as more attractive. They have high pitched voices, so that's going to be a more estrogeny kind of voice and a smaller sounding vocal tract. And so to the same extent that you can wiggle the vocal tract up and down to sound bigger or smaller, some of the research that I'm doing is looking at to what extent we do this either voluntarily or subconsciously in social contexts, either to manage dominance relationships or to sound sort of more attractive in kind of the right context.
Are there other emotions that you study or other people study that have sort of similar relationship between, I guess, the physiology and sort of the social construction that we understand, especially like anger or happiness,
yeah, anger is
joy?
actually the one that came to mind. That's a good one, right? So I think one of the nice things that comes from thinking about psychology from sort of a biological perspective, as I tend to do, is I tend to think about emotions in terms of the problems that they solve for you. So you get angry in contexts where there's a chance of physical confrontation. So it tends to put you in an aggressive mindset, which might be useful in that case. You get additional blood flow to the brain, but also the muscles, especially the upper body, right? So think your face is getting red, your hands get red. So you're deploying energy towards places that they might become useful in the case of this sort of confrontation. You take a posture that makes you look bigger, right? So you get your shoulders puffed out, your chest puffed up, standing erect. So you're trying to look like a big person who maybe someone else might not want to have a confrontation with. And then likewise, when you make an angry voice, the pitch goes as low as it can go, but sound very, very testosterone-y. And the larynx tends to drop a little bit. You try and sound big, right? So you have all these signals pushing in the same direction. Is that you're trying to simulate, a big testosterone opponent that you maybe would not like to have a confrontation with. And if you think of most confrontations that you've seen out in the wild, whether that was in the schoolyard or at the pub, I'm having this conversation from Liverpool, which is somewhat of a rough town. And you see this, downtown now and again. You always get quite a lot of angry shouting before a confrontation. And this is true for humans. It's true for most animals that we've studied, because the actual fight is very, very costly and no one actually benefits from it. Right? Even the winner ends up paying a huge cost to having participated in conflict. So what you do is both sides are interested in solving this peacefully, usually. And so you have these signals that are more or less honestly displaying who's bigger and or more likely to win this confrontation. Mm-hmm. And most of the time, the confrontation doesn't happen, right? It doesn't go to blows. Someone backs off and, one person has probably clearly won and the other hasn't, without coming to blows. And this resolves the conflict, but without the big costs. Where you get a fight actually occurring is when it's not obvious who might win. And so you can't peacefully decide the winner. It has to be done the expensive way. But up until that point, we do a lot of signaling to each other to try and figure out, can we just skip the hard part and one of us has won and one of us is lost?
Okay, that's interesting. Yeah. And then so you would study sort of how correlative that is to dominance, I suppose, is how angry you project yourself to be. And maybe one person's more angry than the other one. The other one's like, okay, you're obviously more angry than me. You're going to take this further, so I'm going to back down. Something like that. Sort of a contest of expression then before the contest of physicality.
Exactly. And so the kind of way that the lens that I tend to think of this through is how honest signals are, right? So if you think of that aggressive context, both sides are motivated to sound as big and scary as possible, to exaggerate as much as they can, and are probably conveying a signal that's quite far away from their honest size and testosterone-ness. And so both sides are injecting a lot of dishonesty into this communicative system, which from an evolutionary point of view is interesting because that means we should stop paying attention to it, right? If you sound more like a more formidable opponent than you actually are, maybe I should stop listening to that. So what we're looking for is, what are the constraints? Is there some floor to how testosterone and how big you can sound? And is that floor related to your real, size? So sure, both sides are sounding as big as they can, and being dishonest and exaggerating, but it's probably the case that the bigger guy can sound even bigger, right, than the littler guy who's trying to sound big. And so you still get some sort of relative honesty out of this. And so that's sort of a lens that I am using quite a lot now, is trying to figure out where the honesty is coming from. Another case actually that we've been working with recently is lying, right? So most of the time, hopefully, we speak to each other and we're transmitting information that we want someone else to know. But sometimes we're speaking dishonestly, right? We're telling things that are deliberately untrue. And we think probably we have some ability to guess when someone's lying to us, even though that person doesn't want to communicate this. So this is kind of the opposite case, right? Where the speaker is trying to destroy information instead of give information. And the listener is trying to dig something out that the speaker doesn't intend to be there. And what we tend to find is actually the best indicator of whether someone is lying is how much they pause. Because this is actually something that's really difficult to control. The thinking is that lying is much more difficult than telling the truth, because the lie isn't de facto plausible, right? You just have to do a bit more thinking to figure out what you're going to say, which means that the liar has a bit more cognitive load, right? They've got to think a bit harder, and it's going to occasionally give an extra pause or two in their speech. So we tend to perceive pausey speech as being less true. And it is also the case that when you lie, you do end up pausing quite a lot more. And so that's an honest signal of dishonesty that's only there because the speaker's having a hard time controlling it.
Yeah, and that intuitively sounds right to me as well. Thinking about deceptive games, maybe something like poker, where you're bluffing sometimes, and sometimes you're honestly promoting your hand. And usually the best strategy is just to take at the same speed, make all your decisions at the same rate. Because if you do something fast, you're probably what's going on. You probably know what your hand is. Whereas if you're being dishonest and you're trying to consider how good your hand is, you don't really know. You take a longer time to consider, just like if you're being deceptive, right? If you're speaking, right? And I think that tracks to what I know about deceptive behavior, I suppose.
Yeah. So actually something that we did recently is we used a really popular deception board game called Secret Hitler. Do you know this one?
I haven't played, but I know of it, yeah.
Yeah, so what we did is when I was working in London at the time, and when London went into lockdown, I was supposed to have a student doing some lab-based study to work on deception, but then lockdowns happened, and there was no way we were going to get people into our recording labs to lie to us and get recorded. And then I went to play board games with my usual group that evening. I was thinking, how am I going to get this student to do this deception study? And then that group wanted to play Secret Hitler, and I spent a couple of hours listening to them lie to me in front of a microphone. And I was like, oh, okay, this is actually a much better experiment than what I had planned. So what we did is we had people playing Secret Hitler through some sort of online forum with a voice channel that we could record. Later, we got to talk to them, ask them when they were lying, when they weren't lying. And then we could go back and measure, right, all those times that you lied, what was your vocal pitch doing and how much were you pausing? And all those times you told the truth, take the same measurements. And then we can see really clearly that for everyone we looked at, they're just pausing so much more when they lie.
Yeah, and so the thing I find interesting about this, we talked a lot about sound production and how things produce sound, like earlier in this podcast. And that's how probably animals evolved to use it first, is there's some things in the environment that we want to gain information from. If there's a predator that's, creeping up behind us, or there's some animal we want to hunt moving in the distance, we want to know what it is and locate it. And that's kind of our sound, is our way of interacting and understanding the world. But humans and other animals, but humans very extensively, have sort of taken this sense and transformed it into this communicative device. And a lot of the way we use our speech is just to communicate things. It's not to necessarily understand the world around us, but to, understand each other in language.
Yeah, I mean, so how language and also how music evolved are obviously very big questions that we don't know the answers to. We do have a good sense that emotion probably came first, if for no other reason than expressions of emotions are strongly conserved, right? So lots of animals express emotions, and they mostly do it in the same way that we do. Right? If you were to encounter an unfamiliar animal, you would probably have a good guess about whether it was being aggressive or frightened, because it's going to make low, big sounds when it's angry or aggressive, and small, diminutive sounds when it's frightened. The same
These
way
are
that we do this,
universal.
right? And this holds across basically all species, as far as we can tell. And so this is probably where these mechanisms start, is that we have these emotional mechanisms that drive sort of basic responses that, okay, so in this context, I'm having aggression, or in this context, I have to flee. And here's all kind of stuff that tends to go along with that, all these useful behaviors and physiological changes that go with that situation. And then maybe we start to layer things on top of that, like, well, maybe you want to start to use that systematically. So for example, if we look at, I forget which species, it might be chimps, or it might be another ape, I forget which one. They have a special call that they do when they find food, right? So we might think of that as an call. Like, nice banana. That they make when they find food. And this is an important part of socialization for them, because they're meant to share food, especially with sort of more dominant individuals. And so this is sort of a more or less automatic thing that happens when they find food, is they make this call. But in some cases, a really cheeky animal might, wander off on his own, find some food, and not make the call, because then he won't be asked to share. Or might go somewhere where there's no food at all, make the call, and then scurry off to another patch as a distraction, right? So you sort of layer on top of these automatic processes that generate vocalizations that are good for the context. Maybe then on top of that, you layer another system that lets you control when these happen, and gives you some voluntary control over this sound production system that we talked about. And so at least I think that some kind of elaboration through that sort of evolutionary pathways, how humans start to get language. How we get to this point, I don't know. But I think it starts somewhere in that direction.
Yeah, and if you want to take it even further, then when we are communicating in language, then I know you study some of the cognitive processes as well. And if you think about speaking, it's this very complex process where you're both producing the sound and listening to yourself at the same time. You have this sort of feedback mechanism where you're constantly modulating your voice and changing it in a way cognitively and expressing at the same time, right? And so that's a big
I mean, so
part
this is something actually that your brain does for all movement planning, right? So you have some intention. I would like to make a certain sound, or I want to go and reach out for this cup. And you've got a set of plans in your brain about how you would move the right combination of muscles to more or less make that work. And so then as it's executing those movements, so making the sound, reaching for the cup, sort of receiving feedback from the muscles themselves, from what you're seeing, from what you're hearing, checking whether the intended thing is actually happening, and then trying to feedback to make it to sort of fix things as they go, and learn how to do it better next time. The thing that's really weird with hearing, which we haven't touched on yet, is bone conduction. So the sound that you hear for your own voice is different than the sound that everyone else hears for your voice. This is also why no one likes to hear recordings of their own spoken voice because it doesn't sound right. There's something weird about it. And the reason for this is that you hear your voice going from your lips through air to your ear. That's how I hear your voice as well. But you also hear your own voice propagating through the bones of your skull, right? So skipping the air altogether, going through the bones directly to those hearing organs we talked about earlier. Bones aren't that great of a transmitter, so they're going to be a low pass filter, which means that at the level of your hearing sort of sensory organs, you get the proper voice signal, plus added on top of that, a low pass filtered version of the same, which is going to strongly bias the percept to being a low, bassy sort of voice, much lower and bassier than you actually are. So then when you record yourself doing a podcast or whatever, you listen to it later, you eventually, God, this is not what I sound like. This microphone must be terrible. I sound like really nasal and, I don't know, full and bright or whatever the descriptors you want to use there are. But it's because that extra channel, that bone conduction channel that you're used to uniquely hearing with your voice has been removed.
Yeah, I've gotten used to it now, but definitely at the beginning. And then going back to that sort of feedback, where you're constantly, getting that feedback, understanding where you're at, and then modulating yourself. But there's singers that basically it's not like playing an instrument where you just hit the note and then that's what comes out. You basically hear yourself produce something, and then there's this very quick feedback to kind of adjust your pitch to get to where you want to be.
Yeah, I mean, that's almost certainly right, because it's a sound being produced over time by an organ that you have sort of continuous control over, right? Whereas if you hit the note of the piano, the note's been struck and that's done. You no longer have any control. That note's finished and we'll live with it. Whereas when you're trying to hit a pitch as a singer, you make an initial attempt at the pitch, and then to the extent that that's right or wrong, maybe you make little adjustments to try and fix it from there, probably quite rapidly, I would think.
And good instrumentalists, good musicians will do the same sort of adjustments as they're hearing themselves play, right? Especially string instruments where there's no clear sort of place to put your finger on the string.
Yeah, right. Then they have sort of a more continuous online control. Yeah, that's a good analogy.
And then did you want to talk about stuttering? Because I was interested in this sort of feedback and how our brain creates the sounds and how we understand as we're producing them. I thought it was interesting. I know you study a lot of the cognitive processes in producing and understanding sound. And this one was interesting to me because there's no physical structure that's causing this. It's some cognitive performance that's creating this effect in people, I guess, this condition.
So stuttering is something that interests me quite a lot as a case where the voice isn't behaving as someone would like it to behave. What we tend to think of as happening is going back to the level of sort of how sound is produced again. Imagine that you were trying to make a sound, but suddenly some of the muscles that were involved suddenly got very, very tense. So that could be maybe the larynx tensing up, or maybe your lips are tensing up. And so now the sound that you intended to come out isn't coming, and it's somehow sort of blocked in place. And then the trouble is, your probably intuitive reaction is to fight through that. So I have some kind of blockage, I'm going to push hard against it to try and get the sound through. But what that does is it makes even more tension and tightens the grip even further. Kind of like those little, those little like finger traps. You sort of put your fingers in a tube and then it clamps down on them, and the harder you pull to get your fingers out, the harder it clamps. It's that kind of thing where it makes a sort of feedback loop where there's tension, so you fight with tension, and that makes it worse and worse. And so what they end up having is instances where, for some reason we don't totally understand, there's a spike in muscle tension, and then this sort of makes a feedback loop that drives them further and further into that tension and then into a stutter. Why this happens is something that interests me quite a lot. We still don't know. So I'm doing a bit of neuroscience work trying to look at brain differences between people who stutter and people who don't stutter to try and figure out how their brains might be different structurally, or how different parts are working differently, or what have you, with the eventual goal of both sort of figuring out just generally what's going on, and then can we use a good knowledge of what's going on to develop better and more useful therapies.
Yeah, so there, like, of course, there are therapies that exist, but they're kind of based on results based or something. Just like this seems to work. There doesn't seem to be this sort of deep level understanding of the process that's going on to create this, and it's a very common condition that people have. Or I'm an American, and Biden used to be a stutterer, right? Just something that a lot of people have encountered in their everyday life, I think.
Yeah, so it's about 10% of children and about 1% of adults stutter. So it's a huge number of people. It's quite a lot. And yeah, so there are a bunch of different therapies. Most of them are good at inducing fluency, but usually by making the person speak in a way that's rather strange. And they like that not very much for different reasons. I mean, a classic one that people seem to know is this idea that, you know, if a person who stutters speaks in a sing-songy voice, they tend not to stutter. And actually, this is interesting for our case because I think I have a guess about why that one works in particular.
Okay.
Which is that so we think about that larynx again, that it's, you know, when it's closed, it makes a pitched sound. And when it's open, it doesn't. It just lets air pass freely. Now, when you speak, you're sort of rapidly moving, shifting between voiced and voiceless positions. So larynx closed, larynx open, right? So think of those the K, the T, and the G. No, sorry, K, T, and P sounds that we made, right? So those need to be made with the larynx open at some point. Whereas all the vowels are made with closed larynxes because you need the voice vibrating.
Yeah.
So that when you speak, you've got this rapid opening and closing of the larynx that's probably a somewhat demanding motor task. Whereas when you sing, any time where the larynx isn't closed is useless. You're not making a pitch. And so you tend to minimize the open time. And so what you have is most of the time, the larynx can just stay closed, and it will occasionally open when it has to, but that's sort of minimized quite a lot, which means that in terms of the complexity of the movements of the larynx, singing is actually quite a lot simpler, right? Just fewer movements, especially these large movements that open and close the larynx are reduced. And so that's why I think singing maybe prevents people from stuttering, is because it's just motorically a bit simpler. That doesn't make it that useful, right? Because at the end of the day, when people stutter in their speech, what it ends up doing is it, you know, makes them feel a bit self-conscious. Yes, they end up communicating a bit slower, but they'll eventually communicate something. It turns out to be much less weird to solve that by just having people be patient and listen to them than to have the person who stutters speak through singing all the time, which is a very unusual thing and causes its own different sort of social problems. And so there's a movement now to start thinking about whether the thing to do isn't so much push everyone through whichever of these therapies seems to be working, because they're not really therapies, they're treating a symptom, really, right? Just make the symptom go away while you're speaking in this strange way. Rather than having them do that, just getting people to be a little more patient with them is probably a lower cost and more effective solution, and just kinder as well. So there's sort of a movement to try and see if we can move listeners instead of move speakers.
Sounds good. I'll get on board with that. That sounds right to me. Maybe if you just want to speak a little bit about some of the future research that you're thinking about, sort of where you see your field of research moving.
Yeah, I mean, so I can give you one maybe preview. There's a technology that has been developing about over the last decade, which is an interesting way to use MRIs, so magnetic resonance imaging machines. People might be familiar with them from functional brain imaging, which is, you know, usually popular with like pop sci sort of stuff, right? Like a way to image function of the brain. You're also maybe familiar with it from like medical dramas or something, where they put people in the big circle scanner and they get a picture of their brain, and so you can see sort of where's the tumor in the brain sort of thing. A much different way that you can use that So if instead of imaging the structure of the brain, right, so a big 3D picture, which is made up of a bunch of slices, taking one after another, just in different locations, instead we take one slice down the center of the head and do that rapidly over time. And what you get is a video of the inside of your mouth and vocal tract while people are talking. And this gives us a way to sort of directly measure movements of the tongue and the lips, the larynx going up and down, that sort of thing. So I'm involved in some sort of tech development to help us get ways of using those data more effectively, because we've had sort of a hard time figuring out what to do with these pictures once they come in, but I have some notions about that. Been doing some development in that direction, and the goal is to have a set of tools that we can use to measure the actual movements of these anatomical structures with whatever behaviors we want. And so for me, the next steps are a lot more to do with size exaggeration. So we have a study coming up where we're going to get lots of people into the scanner, trying to sound different sizes, and then also measure their actual body sizes. So we can sort of map what does, how tall is the person that has, a vocal tract that's whatever, 10 centimeters long. And then if you drop your larynx a little bit to sound bigger, what is the actual size of the person that you're simulating? So we can try and model what the relationship is between these movements that change your vocal anatomy and therefore the acoustics of your voice, and then what those should mean in real body terms to the person hearing that sound.
You're trying to quantify these interactions that people have. That's what it is to be a scientist, I think, is to, you have these ideas that we communicated earlier, but scientist has to quantify it and prove it, right? So that's a much more difficult task.
Exactly. And so yeah, we have these sort of neat new ways of measuring these behaviors. So that's I think where things are going for me.